All right. Welcome to the second talk of today. This talk will be given by Christopher Hojny. Christopher is an assistant professor at TU Eindhoven since October 2019. His main research topic is development of efficient techniques to handle symmetries in mixed integer programs. Besides symmetries, he's interested in theoretical properties of integer programming, for example, the existence of formulations with certain properties, and developing integer programming approaches to solve combinatorial optimization problems. Christopher is also a co-developer of the academic solver Skip, which was recently open sourced. As his background, he did his PhD at TU Darmstadt on symmetry and binary programs, a polyhedral perspective. And he is working on a lot of different quantitative properties of integer programming formulations, such as the relation between the number of inequalities and the size of the coefficients, the relation between the strength of inequalities and the size of the coefficients, or finding the minimum number of inequalities needed in an IP formulation. Many topics that are closely connected to work that Joe does as well. So I think we have a nice theme today. So with that, Christopher, it's all yours.
Yeah, thanks for the very nice introduction, Alex, and also thanks for inviting me to give this presentation. And in this presentation, I want to talk about a very fundamental object in integer programming, namely maybe the core of integer programming relaxations that we want to solve. And this presentation is joint work together with Manuela Prile, Gennady Averkov, and Marco Di Suma. Before we get started, let's maybe fix the setting. What are we usually doing in integer programming? We are given optimization problem, for instance, in combinatorial optimization, and we want to maximize or minimize some linear function. What we then usually do if we want to use integer programming techniques, we come up with an integer programming model, which means that we map the feasible solutions of our problem to integer points in a certain space, for instance, the red points on the left-hand side here. And then our goal is to separate these red points from all the remaining integer points. And for these models that separate the integer points that are feasible from the infeasible ones, different notions of models exist. The leftmost are convex hull formulations or perfect formulations where we want to describe the convex hull of the set of feasible points. This is usually a very hard quantity, and it's usually very difficult to find such perfect formulations. And it is well known that we might need a lot of inequalities to describe the convex hull. To overcome the issue with many inequalities, people have also investigated so-called extended formulations, where we lift our points to a higher dimensional space, compute the convex hull there, where we hopefully can save some inequalities, like in this picture, where we can describe the octagon by an object with 6 facets, and then we project it down to obtain the original object. But in this presentation, I want to leave this world of perfect formulations. I want to stay in the original space. And I'm interested in integer programming formulations that just separate the red points from the remaining black points. And I'm particularly interested in the minimum size of such integer programming formulations. Let's make this maybe a little bit more precise. So in the following, we assume that the set of integer points that we want to describe, capital X, is the set of points, integer points that live inside a polytope P. And the main reason for this is that only for such set of points we can usually guarantee the existence of integer programming formulations, because any such set X is lattice convex, which means in the following that if we compute the convex hull of X and intersect it with the integer lattice, then we can recover our original set X. That is, by building the convex hull, we cannot find new integer points. And an integer programming formulation or a relaxation of such a point set X is then any polyhedron Q that has the property that if we intersect Q with the integer lattice, we recover the point set that we are interested in. And the relaxation complexity is then the minimal number of facets of any such relaxation of any such polyhedron. And related to this quantity, the relaxation complexity is the so-called rational relaxation complexity that we denote by RCQ of X. And this is essentially the same as the relaxation complexity. The only further restriction is that we restrict ourselves to rational polyhedra. And in the following, we're interested whether this quantity, the relaxation complexity and the rational relaxation complexity, is actually the same, or whether there exist integer point sets X for which these two quantities differ. And let's maybe first start investigating this rational relaxation complexity a little bit closer. So suppose in the following that we are given a finite set of points x that are lattice convex, so we can come up with a relaxation. And let's assume that this set is full dimensional, which means that if we compute the convex hull is full dimensional in R to the D. And then it's relatively easy to see that the rational relaxation complexity is at least D plus 1. So we need at least dimension plus 1 many inequalities in any relaxation. And the main argument for this is, suppose it's not the case, so we have at most D inequalities, and the corresponding polyhedron of the relaxation is unbounded. And because we are dealing with the rational relaxation complexity, we are considering rational relaxations, which means that our unbounded polyhedron has an unbounded rational ray. And if we start walking from a feasible point, from our feasible sets of points into the direction of this ray, we will find infinitely many feasible points along this direction. And this is a contradiction to our assumption that we start with a relaxation of a finite set of points. So in a rational relaxation, we need at least dimension plus 1 many inequalities. And motivated by this result, I want to mention 3 questions posed by Keibel and Welke in 2015, which mainly consider a very special set of points x, namely delta D, which is the vertex set of the standard simplex. So the origin and the first canonical d-dimensional unit vectors. And they were wondering whether for this specific, this particular set of points, the relaxation complexity and the rational relaxation complexity is the same, and in particular whether both are at least d plus 1. And more general, if I give you a finite set of points x, a natural question is then whether the relaxation complexity is at least the dimension of x plus 1, and whether in general the relaxation complexity is the same as the rational relaxation complexity. And in this presentation, I want to provide negative answers to all of these 3 questions. Namely, we are going to show, together with Manuel, with Marco, and with Gennady, that already in dimension 5, there is actually a difference between rational relaxations and irrational relaxations. The rational relaxation complexity of delta 5 is 6, whereas for irrational relaxations, we can come up with formulations that use at most 5 inequalities. And now that we know that there's actually a difference between the rational and the general relaxation complexity, we might also wonder about the difference of these 2 quantities. And we can show that the relaxation complexity of delta D grows sublinearly. And in this presentation, I want to provide you some intuition why these results are actually true. But before I go into the details, are there any questions regarding the setup? If that's not the case, so then let's maybe start before we talk about the details of the proof. Why do we actually care about the simplex? And the main reason is that the simplex turned out to be rather rebellious, because for any kinds of techniques that we tried to tackle the simplex, they did not work out. And in the beginning, we thought there cannot be a difference between the relaxation complexity and the rational relaxation complexity. So to show that the relaxation complexity and the rational relaxation complexity is actually the same, let's try to come up with some tight lower bounds. And how can we come up with lower bounds? We consider a sequence of lower bounds on the relaxation complexity, which are based on the following idea. We start with a set of integer points x and a superset of this integer point set x that we call y. And then we are interested in finding relaxations of x with respect to this point set y, which means that if we are given a relaxation P and intersect it with a larger point set y, we can recover the original set x. And by RCx of y, we then denote the minimum number of facets of such a relaxation of x with respect to y. And because we restrict ourselves to a subset of the integer points, it's easy to see that the relaxation complexity of x with respect to y is a lower bound for the relaxation complexity of x. And then it's natural to start with a small subset y and then grow this subset to eventually, hopefully, show that we derive with a relaxation complexity. However, as I said, the simplex is rather rebellious, and we could show together with Matthias Shimura that if we take an arbitrary finite set of points y from that we want to separate the points in the simplex, then any such relaxation with respect to y has at most roughly dimension divided by too many inequalities. And in particular, for dimension 5, this bound shows that in any relaxation with respect to a finite set of points y, we need at most 5 inequalities. And this made us suspicious, and we thought, maybe the relaxation complexity and the rational relaxation complexity are actually not the same. And in the following, I want to show how we prove this. To be able to do so, we need to introduce yet another version of the relaxation complexity, which is now not restricted to integer points, but to arbitrary sets of points. And these points are again denoted by x and y. And we call a polyhedron P a relaxation of x within this general set y, if again the polyhedron intersected with the set y recovers the set of points x that we are interested in. And again, RC x of y is then the minimum number of facets in such a relaxation. And in the following, we will focus on a very specific choice of y, namely of set of mixed integer points, where we have d coordinates in our point sets that are assumed to be integer, and n coordinates that are arbitrary, continuous, real numbers. And in particular, if we restrict ourselves to mixed relaxations in which n is 1, we can interpret this additional continuous coordinate as a height of a lifting of integer points, which means that if we are given a set of integer points x, then we can define a function h that assigns each of these integer points a real value that we can interpret as a height. And then we can consider this mixed integer set of points as a tuple that consists of the original integer point plus its height value. And it will turn out to be useful to consider in the following also the convex hull of the lifting of these sets of points, which I denote by C lift h of x. A natural question is then, of course, if we are considering these mixed relaxations, how can we actually find mixed relaxations of a set of points? And here it turns out that we need to consider the convex hull of the lifting that I mentioned on the previous slide. So suppose we are given our set of integer points x, which are the red points in this picture here, and we assign each of these points a height value, which leads to the blue points, and we compute the convex hull. Then we distinguish two kinds of facets, namely the upper facets, which are shown here in blue, that is, whose normal vectors point upwards, and the lower facets, which is in this case the red facets, that point downwards. And we can show that if we are given a full dimensional polytope P and a set of integer points T, that is non-empty, and we assign each of these points a height value, then the polytope P is a relaxation of this lifting with respect to the k integer coordinates and the height value in the last coordinate, if and only if for every of these lifted points, for every of the blue points, we can find an upper and a lower facet of the relaxation P that contains this point. So for instance, if we consider this blue point here, then this blue facet and this red facet both contain this point. And if we project the higher dimensional object onto the first k integral coordinates, the projection of this polytope needs to be a relaxation of T with respect to the integer lattice. And this is an if and only if condition. And based on this observation, we can now also derive a mechanism to come up with mixed relaxations of a set of lifted points, in which we essentially need to compute the convex hull. We distinguish the facets by the ones that point upwards and point downwards, which can be done by considering the facet-defining inequalities and distinguishing the facets based on the sign of the or the height value. And then there might also exist some facets that point sidewards, and they refer to them as lateral facets. And based on the observation from the previous slide, we can come up with a relaxation of this lifting by considering coverings of the points in our lifted space by upper and lower facets. So we are looking for a collection of blue facets that contain all the lifted points. And we are also considering a collection of lower facets, the red facets, that contain all these points. And then we need to select these facets in such a way that we can cover all these points for our polyhedron from the previous slide. And of course, based on the argument on the previous slide, it's sufficient to consider a covering that consists of the minimum number of inequalities, because this will suffice for coming up with a relaxation. And we refer to these two numbers, the minimum size of an upper covering and a lower covering, as the upper covering number UCN and the lower covering number LCN. And using this observation, we can then derive a mixed relaxation of a lifting of integer points by considering a relaxation with respect to the red points. That is, by coming up with some relaxation with respect to the red points in the original space, which we then will lift trivially to one dimension up by setting the value of b to 0, which will lead to some lateral facets. And then we take facets from the upper covering and the lower covering to come up with the remaining inequalities that we need to define a relaxation based on the result from the previous slide. And this inequality will be the main tool for showing that or one of the main tools that the relaxation complexity and the rational relaxation complexity differ. So what do we do in dimension 5? In dimension 5, we start actually not with a simplex, but with a unimodularly equivalent version of delta 5, which makes the calculation a little bit easier. So we keep the first standard unit vectors, we keep the origin, and we replace E4 and E5 by these two vectors here. And then we consider a very special relaxation that has already been investigated by Keibel and Weltke. Namely, they consider the irrational line that is spanned by this vector here. And then they show that if we add this line to every point in the convex hull of delta, that we can come up with an unbounded relaxation of our simplex delta. However, this result is not sufficient yet to show that the relaxation complexity is at most 5, because this relaxation has 6 inequalities. But we will modify this relaxation slightly to come up with our result that actually shows that the relaxation complexity is at most 5. Namely, we project this set of integer points along this line to a 4-dimensional space, which is formally defined by this map here, pi. And now let's assume that in this projected space, we are given a polyhedron that is a mixed integer formulation of the set of projected points. And we can then show that by embedding this polyhedron in 5-dimensional space by assigning it a trivial height value of 0 and adding the irrational line again, we obtain a relaxation of the original set of 5-dimensional points delta. So we project the polyhedron to a lower dimensional space, we identify a relaxation in this lower dimensional space and lift this relaxation to the higher dimensional space to come up with a relaxation in the original space. And by doing so, we can relate the relaxation complexity of the original set of integer points with a mixed relaxation complexity of a set of projected points, because this construction yields a relaxation for the mixed integer set of points. So the only thing that we are now left up with is we need to be able to construct a mixed relaxation for the set of projected points that uses at most 5 inequalities. And then by some experiments, we came up with such a set of inequalities. I don't want to talk you about through the details of these inequalities, but you can show that the only mixed integer points that satisfy these inequalities are actually the points in the projection. Okay, and now we have all the pieces together, and we can show that the relaxation complexity of delta 5 is actually 5. We start with this inequality that I presented on the previous slide. We now have the constructed set of inequalities that leads to a mixed relaxation of the set of projected points. So we know that this quantity here is upper bounded by 5. And to show that this bound is tight, we need to come up with a matching lower bound. A trivial lower bound on the relaxation complexity of delta 5 is the relaxation complexity of delta 4, because if we take a relaxation of delta 5 and intersect it at height 0, we get a relaxation of delta 4. And in 4-dimensional space, Avakov and Shimura proved that there is no difference between the relaxation complexity and the rational relaxation complexity. And for this reason, this value needs to be exactly 5. And this is how we show that the rational relaxation complexity and the relaxation complexity of delta 5 is actually different in dimension 5. And to prove the sublinear bound, the second result that I mentioned in the beginning, we essentially use the same construction, but we generalize it, and it becomes a little bit more technical. So let's try to summarize the steps in our proof. What did we do first? First, we considered a unimodular transformation of the simplex, and we projected onto a space with a dimension less. And then we were looking for a mixed relaxation of this set of projected points. And we can interpret this last coordinate, the continuous coordinate, again as a lifting value from a three-dimensional space. So let's visualize this. We start with the set of points that we are interested in, delta 5. We slightly modify them by replacing the last unit vectors by a unimodular transformation, which leads to a simplex to a set of points with this structure. We again have a diagonal, but above the diagonal we might have some non-zero entries. Then we project these points onto a lower dimensional space, and we interpret this last coordinate as a height value, and then we derive a mixed relaxation with respect to this set of projected points. And we generalize this idea also for arbitrary dimensions, but for the sake of simplicity, let's assume in the following that the dimension of the points that we are interested in is 2 to the k minus 1. We again start with delta d, the simplex in dimension d. We then construct a unimodularly equivalent simplex to make the calculations easier. And in this case, we consider a simplex of dimension k, which corresponds to the first columns here, which we then naturally embed into a higher dimensional space in dimension d. And the remaining unit vectors are again replaced by a unimodular transformation in such a way that we find all the possible binary vectors that have at least 2 non-zero entries above this line here. And we can do this actually because of the choice of the dimension that we have here. The reason why we do so is if we now project the simplex delta d prime onto the first k coordinates, and in this way we can, I should mention this, we decompose the simplex essentially in two simplices of different dimensions. And this will be useful in the following. And the reason why we use this unimodular transformation is because now we can control the projection of the simplex very easily, because if we now project everything onto the first k coordinates, we get all the different possible binary vectors. And then our goal is to assign a proper height value to these projected vectors. And the reason why we need this height value is because we did not find an immediate relation between the relaxation complexity of this modified simplex delta d prime and its projection, and assigning a lifting or a height value to these integer points will allow us to restore some structural properties. And the main technical lemma that allows us to do this is the following. So suppose we are interested in describing the integer points in delta k, but we are also given another set of integer points y that is disjoint from delta k. Then we need to select a height function that assigns each of these points a value. So in our previous example, these are all the binary vectors in k-dimensional space. And if this height function satisfies some properties, then we can show that the simplex that lives in dimension k, the dimension of the projected space, plus the number of integer points that we add to this projection. If we are interested in the relaxation complexity of such dimensional simplex, then we can relate this to the mixed relaxation complexity of a certain lifting of these integer points that we have selected. And of course, the choice of the height function h is not arbitrary. We need some structural properties. And the properties that we need is that we assign all of the points from the simplex, delta k, a rational value. And the remaining height values need to be irrational numbers that are linearly independent over Q and that are in particular linear independent with 1. And by imposing this property, we can then show that this inequality holds. And this means, because our lifting from the previous slide was selected in such a way that we can recover all the binary vectors in k-dimensional space, we can relate the relaxation complexity of a d-dimensional simplex with the relaxation complexity of a lifting of the hypercube. And then using this, the previous result that allows us to come up with a relaxation, a mixed relaxation of this set of lifted points, we can upper bound the relaxation complexity of delta d prime by the relaxation complexity of the hypercube and the upper covering number and lower covering number of the lifting of the hypercube. Of course, it is very difficult to investigate such kind of liftings because we have these irrational coefficients. And our idea was then, okay, maybe we can start with a rational lifting of the hypercube and then slightly perturb it by adding some irrational noise to turn it into actually an irrational lifting. But this approach has some difficulties because if we start with a rational lifting that looks like this and we add some noise, the facet structure might change of the lifting. And this means we cannot really control the upper covering number and lower covering number of the facets of this lifting by adding some irrational noise if we do it in the wrong way. But we could show that if we do not consider arbitrary facets of the lifting, but simplicial facets, then if the lifting function is not a restriction of an affine function and the irrational noise is relatively small, then simplicial facets of the lifting will remain simplicial facets. And in this case, this means that we need to weaken our upper bound by not considering arbitrary covering numbers. So we restrict ourselves to coverings containing of simplicial upper facets and lower facets, which leads to the quantities SUCN and SLCN. And doing so because we take our inequality from the previous slide and we weaken and we strengthen the requirement on the covering numbers, we get a looser lower bound on the relaxation complexity. But in our case, it turns out that this is sufficient. Then, of course, we need to select a suitable height function. The height function that we select is this one. If you're a little bit familiar with triangulations, this height function here might ring a bell. It's the height function corresponding to the staircase triangulation, and we modified in the last coordinate by assigning it a positive or negative sign depending on the value of the last coordinate. And for this specific choice of the height function, we can show that there's actually no difference between the simplicial upper covering number and the simplicial lower covering number. So this is nice because we only need to consider one quantity. And then because I don't have the time to provide the details, we investigated how many inequalities, how many simplicial facets do we need for an upper covering and a lower covering. We consider two cases in which we distinguish the upper facets by the lifted points by the last coordinate. And by associating the simplicial facets with certain objects in the Hasse diagram of a suitable poset, we can show that we can cover all the lifted points with the last coordinate having value 1 by at most 2 to the k divided by square root of k many simplicial upper facets. And with a related problem, we can also show that we can cover the points with a 0 coordinate in the last coordinate by sufficiently few simplicial facets. And by combining these results, this shows that the upper covering number of the hypercube with respect to our specific choice of the height function is upper bounded by a big O of 2k divided by the square root of k. And now we have all the ingredients together that allow us to show the upper bound result. We take the inequality that we have seen for quite some time. We compute the first quantity here, which is known by a result of Weltke, that the relaxation complexity of the hypercube is exactly k plus 1. We take our big O bounds for the simplicial upper and lower covering numbers, which is 2 to the k divided by square root of k. And by the specific choice of our dimension d, which is essentially 2 to the k, we can show that the relaxation complexity of delta d is upper bounded by d divided by the square root of log d. I know this was a pretty technical presentation, but I hope that I could give you some impression on the tools that we use to prove our asymptotic upper bounds. And of course, this leads to some open questions. For instance, whether our upper bound is tight or whether we can improve the upper bound on the relaxation complexity of delta d. We can also ask a more general question, namely, can we characterize the finite sets X such that the relaxation complexity is actually less than the rational relaxation complexity. And in particular, we might wonder about the minimum value of the relaxation complexity that we can achieve. And of course, we are still not aware of any algorithms that allow us to compute the relaxation complexity or the rational relaxation complexity in arbitrary dimensions. And we will be very interested in actually coming up with such algorithms. And that's all what I wanted to talk about. Thank you for your attention.
Thank you, Christopher. I think in the interest of time, what we'll do is we'll leave all the questions for the breakout rooms. So what I'm going to do now is I'm going to, well, first of all, I'll stop the recording. So thank you everyone who's watching in the future.